Members, we are back in our chemistry, and this chemistry today we are going to look at what we call group 7 elements. Group 7 elements, there is a lot of chemistry we can talk about group 7 elements. However, we are going to pick some specific areas which are very, very vital and always maybe becomes very hard for you to understand them. So remember, group 7 elements, we have iodine, we have bromine, we have chlorine and fluorine. However, when we are looking at the group, we shall begin with fluorine, chlorine, bromine, and iodine, mainly. This group, we are calling it a group of halogens because these are salt makers. From Latin, we shall see that halo means what? Salt. So salt makers. So today, I'm going to consider first what we call the boiling points of group what? Of group 7 elements. When we are looking at the boiling points, we are looking at now their ease to turn to vapor state, their volatility. So mainly here, we are looking at how can they change to vapor state. So the boiling points of group 7 elements, we are going to see that the boiling point just increases. Boiling point increases down the group. Increases down the group. Members, when you are going to consider the increasing boiling points of group 7 elements down the group, our main focus is going to be on the following keywords. These ones are very, very vital. You will first know, first of all, that group 7 elements occur as simple molecules. They occur as simple molecules. So when I say simple molecules, this one implies that they have molecular structures. Simple molecular structures. And these molecular structures now, remember molecules always are held by intermolecular forces of attraction, which we are calling the van der Waals forces. Now, the strength of the van der Waals forces, mainly based on what we call the molecular mass, the magnitude of the molecular mass, or the molecular weight. Can be molecular weight. So, what are we seeing with group 7 elements or halogens? We are seeing that as you're moving down the group, these simple molecules now, their molecular mass increases. We see increasing molecular masses as you're moving down the group. What are we saying? You'll discover that fluorine at the top is smaller. Then iodine at the bottom here. So we are seeing a trend like that. Iodine very big, fluorine very small. Meaning the molecular mass of iodine is bigger. Then the molecular mass of fluorine is smaller. So when the molecular mass increases, the magnitude now, molecular mass, its magnitude, when it increases, we see that even the strength of the van der Waals forces increases. When the strength of the van der Waals forces increase, it means the molecules cannot easily be broken down into gaseous what? Into gaseous state. And that one means you need to put in a lot of what? A lot of energy. And as you are putting in energy to break them, it means you are going to increase what we are calling the boiling what? The boiling point. So, coming back here, we are saying, members, the boiling points of group 7 elements increases down the group. Why? We are saying, 1, group 7 elements exist as simple molecules, therefore having simple molecular structures, and the simple molecular structures are being held by van der Waals forces of attraction, which van der Waals forces of attraction, their magnitude depends on the molecular mass of the molecules. So down the group, there is an increase in the molecular mass. When you increase molecular mass, you increase the strength of van der Waals force. Then when you increase the strength of the van der Waals forces, you need a bigger what? Bigger energy. And when you need bigger energy, you see boiling point is going to increase down the group. So these keywords should be taken into into consideration. Members, for group 7 we are considering van der Waals forces and molecular mass. This one doesn't mean that even group 2, if we are looking at group 2, we shall talk about van der Waals forces. For group 2, when we reach there, we shall talk about metallic what? Metallic structure. Metallic structure. And that metallic structure, our main focus will be on the strength of the metallic what? Metallic bonds. Take a note of that side that you don't confuse this chemistry of group 7 with the chemistry of group 2. Then, or chemistry where there are metals. Then metallic bonds and the strength of metallic bond will depend on electrons. Electrons contributed to the crowd. Electron what? Electron crowd. Similarly, when you come to group 4 members, when you reach group 4, don't say that we shall talk about van der Waals forces. Group 4 we shall look at, for example, carbon having a giant tetrahedral structure. For carbon, for group 4, you have tetrahedral structure made up of numerous covalent what? Bonds that cannot easily be broken down. But when you come to silicon steel, you talk about giant tetrahedral structure. But as you are moving downwards to germanium, lead and tin, you will discover you are dealing with what? Metallic structure. So take a note of the side that you don't confuse the chemistry. So that is our beginning point on the boiling points. Now when we leave that, we are going to look at what we call the boiling points of the hydrides or the halides of group 7. Halides. These halides you can talk about like HCl, you can talk about like hydrogen bromide, hydrogen fluoride, hydrogen iodide. Those ones, hydrogen iodide. Those ones we are calling them the halides now, or the hydrides. Now, when you look at the boiling points of these hydrides members, you are going to discover that the chemistry of these halides or hydrides is mainly basing on what we are calling the magnitude of the van der Waals forces. Remember, these are molecules. These are molecules. The molecules. So they have molecular structure. This is molecular structure. This molecular structure. The structure now, it means the molecular structure is being held by van der Waals forces. Van der Waals forces. Which van der Waals forces we said its magnitude? Magnitude of van der Waals force, we said it is depending on what? Magnitude of van der Waals force. We said magnitude of van der Waals force depends on what? Molecular what? Molecular weight. Molecular weight. So we have molecular weight there. Now this implies what? That as you're moving down the group, you can see from HCl now, if you are going to consider HCl, that one is having a smaller molecular weight compared to what? Compared to hydrogen bromide and compared to hydrogen what? Hydrogen iodide. This implies that I'm first of all putting hydrogen fluoride aside. I'm going to give you a reason why I'm putting it aside. I'm considering these ones first. You are going to discover that the boiling point is going to increase from hydrogen chloride, hydrogen bromide to hydrogen iodide. This one will be having the greater boiling point, and this one will be having lesser. That one considering HCl, hydrogen bromide, hydrogen iodide. The reason which you are going to give here for the increase of the boiling point from hydrogen chloride to hydrogen iodide is going to be now that the strength of the van der Waals forces is going to increase as you are moving down the group, because the molecular weight is increasing down the what? Down the group. Due to the fact that these ones they are molecules in nature. So when you are reasoning the reason as to why the boiling points are changing like this, increasing from HCl to hydrogen iodide, you are going to base it on the van der Waals forces. You are going to base on the magnitude of the molecular mass, and so on. Now, when you come to this member, hydrogen fluoride is unique members. We expect now its boiling point to be lower. But again, we discover that anomalously, it is having a higher boiling point. Actually, it exists as a liquid at room temperature, yet these ones, all of them, are existing as gases. These ones are gases in nature. Gases in nature. All of these are hydrogen chloride, hydrogen bromide, hydrogen iodide, gases. But again, hydrogen fluoride is unique, a liquid. Why a liquid? Now we are going to come to this to this chemistry, we are going to discover that the boiling point of hydrogen fluoride actually is the highest. Extremely high, abnormally high. That is anomalous in nature. Why is it like that? The reason we are going to give here one, fluorine in hydrogen fluoride is small. Fluorine being small, we are seeing that fluorine is highly, being small, is highly electronegative. Being highly electronegative, it implies that fluorine can attract the bonding electrons. Then when it's attracting bonding electrons away, or what we call the negative inductive what? Negative inductive effect. That is negative inductive effect. Now we are going to result into formation of what we call hydrogen what? Hydrogen bonds. Which hydrogen bonds are we saying? You will discover that our fluorine here, because it's pulling electrons, so it shall create what we call a dipole. Fluorine is like that. So it is small and is attracting electrons toward itself like that. If it's attracting electrons toward itself, what are we seeing now? We are seeing that this one is going to become a negative and this one is going to become a positive. So we create what we call a dipole. This is now one hydrogen fluoride molecule. Then when you have another hydrogen fluoride molecule near this, you're experiencing the same situation with the positive there and negative there. You are seeing from principles of physics, we have some electrostatic force of attraction in between the fluorine here and this hydrogen. And now this kind of arrangement here is what we are going to call an hydrogen bond. Now, because of the presence of the intermolecular hydrogen bonds, actually call them intermolecular, because of the presence of intermolecular hydrogen bond, we see that these bonds are stronger compared to van der Waals forces. In the first members, van der Waals forces we talked about in these members, the van der Waals forces are weaker in the other hydrides. But the hydrogen bonds are stronger. Therefore, because they are stronger, they cannot easily be broken down. So this one requires a bigger energy in hydrogen fluoride. Because you need bigger energy in hydrogen fluoride, this implies why there is an increase in its boiling what? In its boiling point. So take note of that. Now this chemistry doesn't only apply to hydrogen fluoride. Remember, this chemistry of hydrogen fluoride, we can also apply it somewhere, like in water. Remember, even when you count group 6, you'll find that you have hydride of water and you have even hydride of sulfur. You'll discover that this one is a liquid and this one is a gas. The chemistry is the same. Why? See, even here you're going to form hydrogen bonds. Don't forget that even here you have hydrogen bond because of this one being highly electronegative, it attracts electrons and you have a positive there, If now we have another molecule for water here, like that, for example, experiencing the same situation like that, you find that we are going to form now a bond there, which we are calling an hydrogen what? An hydrogen bond. So we have an hydrogen bond there. Even here can form a hydrogen bond. This explains why these ones are hydrides of group 6, but this one is a liquid, this one is a gas. High boiling point, low boiling point. Beg your pardon. This is high boiling point, low boiling point. The same chemistry is the chemistry you are applying when you go in organic chemistry under 2-nitrophenol, and 4-nitrophenol. This 4-nitrophenol will have a higher boiling point because of intermolecular hydrogen bond, and this one will have low boiling what? No boiling point. So I want you to grasp that content properly. Now, members, we are done with our boiling points of the halides. Now I want to look at the acid strength of these halogenal acids. Halogenal acids, we have hydrogen iodide, hydrogen bromide, HCl, and hydrogen fluoride. Now, when you come to acid strength, first of all, acid strength, we are going to base on the concentration of the protons from the acid. How do you get the concentration? That one is rising from the degree of dissociation. Degree of dissociation of the acid. Degree of dissociation is seen in the ease of giving out proton. Ease of giving proton. So the ability to give away the proton you have by this group 7 acids will depend on the strength. Depend on the strength of the hydrogen allied bond. The more stronger it is, the less are the chances of giving a proton, and the weaker the acid will be. Then the more weak it is, the higher the chances of giving a proton, and then the more stronger the acid will be. Now the strength of the acid, the hydrogen bond, or the hydrogen allied bond, is mainly now basing on what we call now the electronegativity of the halogen. Halogens which are less electronegative, the bond is weaker because the bond will become less polar. So we are seeing now the order of the bond strength between the hydrogen, halogen, is going to become now, our order is going to become hydrogen fluoride will be having a greater strength of the bond, this one, and then this implies that this one is having lesser strength of the bond, and this one is more stronger. When it is more stronger, it means it does not easily give away its hydrogen, and if it is less stronger, it can easily give away its hydrogen. Now, after seeing this implies that now the acid strength is going to become that hydrogen iodide is going to become a stronger. That is a stronger acid. Why a stronger acid? It is having a weaker hydrogen allied bond. When it is weaker, can easily release the what? The proton now. Can easily release the proton. Now, but when you come to hydrogen fluoride is going to become a weaker acid. Why weaker acid? Stronger bond. Why stronger bond? We talked about it. It is highly electronegative. This one is, the fluorine is highly electronegative and is attracting bonding electrons, and now we are seeing some dipole making the bond more polar, stronger. But for this one, hydrogen iodide, it is less electronegative. Remember, electronegativity is going to decrease as you are moving down the group. So we discovered the iodine in hydrogen iodide is less electronegative. Therefore, this bond is going to become more covalent and can easily break down to release this proton. Now this one is going to make this one a stronger acid, hydrogen iodide, and this one to become a weak acid. So they can tell you to describe acid strength. You are going to base on, now the order is going to be like that. This one is the order of the acid strength. You discover that this is our order now. That is our order of the acid strength. Why are we taking this order? Try to focus a lot on this order. This is acid strength. We are saying this one is more acidic, this one is less acidic. Why? As you are moving down the group, electronegativity decreases. When it decreases, the bond between the hydrogen and the halide becomes, as you are moving down the group, becomes increasingly weaker. And as it is becoming increasingly weaker, it can easily release the hydrogen. You easily release the hydrogen, it means this one is like this. You are halogenal acid, and you are easily giving away your proton, plus now the halide ion like that. So this one now is going to increase down the what? Down the group. That one is increasing down the group. As simple as that. That is our chemistry of the acid strength. Now members, from there, let us try to look at now what we are calling the oxaloacids of group what? Oxaloacids of group 7. Remember, oxaloacids are many. An oxaloacid, that one implies just an acid having hydrogen oxygen, and another element. So our concern today, we are going to look at those ones having hydrogen, oxygen, and chlorine. Those are oxo acids. What matters in these acids, there are majorly 4 types of the acids formed by the group 7 elements. And now the first one, for example, if I'm going to consider chlorine, I'm going to base on chlorine to paint a good image of these acids. Because all elements are forming, even apart from fluorine forming only one, the first one. But the other elements can form all of them. So I'm beginning with what called hypochlorous acid. This hypochlorous acid is now the first oxo acid. As we are saying, the first acid is going to be this one, hypochlorous acid. So the ion can be like this. Then we are saying it is linear shaped. The oxidation state is going to be 1. Where are we getting the 1? For example, if we are here, I'm just going to relate from the formula here. If now oxidation state we are counting for chlorine. So assuming oxidation state for chlorine is X, we rate that oxidation state for chlorine is X. So we can get our X there. When we get our X, then we are going to add there the oxygen. Oxygen, remember, is having negative 2 when you go back there to the valence. So you have negative 2 here, meaning that is plus negative what? Negative 2. And when you add negative 2, then you have this one here for hydrogen. Hydrogen is having valence of positive 1. So we have plus 1, which is equivalent, the overall charge on the molecule is 0. So when you compute the X plus negative 2, obviously you are seeing what is going to happen here. So you discover that you are going to obtain your X is equivalent to positive what? To positive 1 as our oxidation what? Oxidation state. Now the second acid, we are calling it chlorous acid. This chlorous acid here, the formula is like that. The formula, after knowing the formula, we can also compute the oxidation what? The oxidation state. How are we going to compute the oxidation state? Now we have our chlorine being X, let us assume is X. Then your X, you add there, how many oxygens do you have there? You have 2 oxygens. That means that is negative 2 times 2. For oxygen valence, for oxygen or convalence times 2, the number of oxygens. Then plus the 1 for hydrogen. This one here, that is 1 times 1. All of it is equating to what? To 0. So when you look here, you discover you have X plus negative what? Plus negative 4, then plus 1 is equivalent to 0. The mathematics here you're going to apply is the primary mathematics to solve for X. When you solve for X, you are going to get your X is equivalent to positive what? Positive 3. Now, there are cases where they can give you the chlorite ion, this one here, and they try to find the oxidation state. Similarly, you are going to rate here. You are going to, now we are calculating for this one. Also, it's going to become 3, but we are trying to calculate. You will find still it is X for chlorine, then plus what? Plus your 2 oxygens there. Remember, oxygen we said is negative 2 times 2. Don't forget that. Then plus what? Hydrogen is not there, so you're not adding anything. So ion is going to be like that. It's going to be like that. Remember the chloride ion. So when you are calculating now, we are having our 2 oxygens. We are saying negative 2 times the 2 oxygens. Then we are going to say this, all of this one is equivalent to overall charge here. Because remember, let me make the thing clear. The thing is like that. So the overall charge here is negative what? Negative 1. So applying mathematics here, you have X plus negative 4 is equivalent to negative 1. Apply all of mathematics or primary mathematics. You will take it down. This one is going to become a positive the other side. You cross it the other side. When you cross it, you're going to obtain your X is equivalent to positive what? Positive 3. That is oxidation state. Now the shape we are going to obtain what we are calling a V shape. V shape from where we are having now our chlorine in the center here. That is our chlorine. Then you have your oxygen. Oxygen is, you have how many? Try to look at oxygens. We have 2 oxygens there. So you have the first oxygen here, and you have the second oxygen there. But remember, oxygen must be bonded to 2 bonds. So this one, if we are going to bond it to 2, then this one also, we have 1 bond, so we are going to bond it, the second bond there. So you have 2 bonds for oxygen. This one, then these ones. But remember here, we should remain with the lone pair of electron here. we are going to have a lone pair of electrons there. Now from there, there's not only one lone pair, we have actually two lone pairs. I'm going to show you why we are talking about lone pairs. So from there, this shape is going to become a V shape, like that one of water. Or you can even call it a bent shape. Then from there now we are going to look at the other acid. Our other acid is going to be the chloric acid. Our chloric acid you are going to discover. Let us try to find the oxidation state before we write it there. So we are going to say we have our chlorine, we are writing it to be X. When you write it to be X, you have how many oxygens? There are 3. Then oxygen we said is a -2, so you have -2 times the 3, then plus the 1 for this one, because it is having valence 1 hydrogen. So that is plus 1, which is 1 times 1. Then all of it is equivalent to what? To 0, the overall charge. Now we'll discover that we have X plus -6 here, plus 1 is equivalent to 0. When you apply the mathematics here now, you will find that you have X minus what? Minus 5 here is equivalent to 0. So this one is going to cross the other side. Our X is going to be equivalent to positive what? Positive 5. Don't forget that. So meaning oxidation state of this acid is positive what? Positive 5. They can ask you to calculate for this one, the chlorate ion. You are going to do the same. You're just going to say still X for the chlorine plus the -2. For this one here, we are calculating for the chlorate. This one was there, then times 3. Obviously, is equivalent to -1. So this one is going to become now -6 plus -6 is equivalent to -1. Now, you look here. We are just going now to make this one to cross the other side. It's going to become a positive. When it crosses, we shall have X is equivalent to -1 plus positive what? Positive 6. Positive 6. And obviously, we are going to come back to X is equivalent what? To 5 for this acid. Now, the shape of the acid is going to be a trigonal what? Pyramidal shape. So we have our chlorine there, having a lone pair of electrons. Then we have our oxygen. Oxygen there are 3. Then you have another one there and another one there. Oxygen is like that. But these ones you are going to give them 2 bonds. Then this one we have 1, another one is having like that. So this one we are going to say it is a trigonal what? Pyramidal shape. However, even if they have not put this one, you draw the same thing. They always ask you that. Even if you have not put this one, you draw the same thing. And so on. Now, let's say we come to this acid here. This acid here, we can also compute oxidation state. When you follow the same mathematics you have been following, remember as you are going to get positive 7 here. Follow it up. This one means you are relating this one to be X, for instance, plus how many oxygen? That is 4. That is now -2 times 4. And then plus the 1 of hydrogen is equivalent to 0. So when it's equivalent to 0, obviously, you'll find that you have X plus -8 here is equivalent to 0. And finally, you are going to take this one. So you have plus 1. Don't forget that, plus 1. Then is equivalent to 0. Is equivalent to 0. So when you see this one now, you have -7. Of course, here you have X plus -7. And it will go the other side. And you come back mathematically to this point of positive what? Positive 7. The shape, this one is going to be tetrahedral. Tetrahedral, we are going to see that we have now 4 oxygens. Chlorine is the center. So you have 1 here, you have 1 there, you have another one there, another one there. So you have 4 oxygens, 1 there, 1 here, 1 here, 1 there. Remember this one is having hydrogen. Then this one means there are 2, like that. And this one is going to become a tetrahedral shape. Now let me try to show you how these acids are formed. There is some bit of covalence and dative bonds here before I go. So when you look at our structure here, there is a double bond also there, members. We have a double bond there. Now, after clearing all the structures here, I want to show you one acid how it is formed. Now, members, we have already seen our linear structure, our V shape, our pyramidal structure here, our arrow was missing there, pyramidal structure. Then we are seeing our tetrahedral structure there. Now we want to reflect how this one is formed. Now when you look at the chemistry of forming these structures, we have to bring in the chemistry of what you call the lone pairs. Lone pairs just those electrons which are redundant, which are doing nothing, the bonding. So here we are going to take a situation of our chlorine. Remember chlorine is 17. Chlorine being 17, when you go back to O-level configuration, you'll discover that the configuration is 2 to 8 to 7. Now when we bring the other alphabet arrangement, we are going to say that this one is 1s2, then 2s2, then we have 2p6, then we have 3s2, 3p5. Now, we are not going to consider all of this one. This one is going to act as the core structure. Then this one is the valence structure, which I'm interested in. Now, our valence structure there, in our valence structure, you discover that if you are going to distribute them based on what Pauline said and Hindu, you discover that this 3s, if we have our 3s here, that is 3s, occupied by 2, I'll put these 2 electrons there. Then, when you are going to bring the 3p, this is our 3p, but our 3p is accommodating 5. This implies what? That at the start, we can put, remember Hindu said you first fill the orbitals singly, then you have a balance of 2, then you can pair up those ones like that. Now this implies that the best way how chlorine can bond, chlorine must use 1 electron. Remember we said the 1 electron, that is the valence which it uses, and actually you can say that it uses 1. And now when you look at the first compound here, or the first acid, the hypochlorous acid, that one is using 1 electron. 1 electron, when it is using 1 electron, you will discover that now, if I'm putting here the chlorine in the center here, and then I have, assuming this is my chlorine, which is using 1 electron here, and is going now to bond with oxygen here. Let me assume this is my oxygen. Remember, oxygen is having 6 electrons here. 6, when you go back to O-level chemistry, those are 6 what? Electrons. Then it is demanding how many? It is demanding 2 electrons. So the chlorine will now bring it C1 here. At the same time, when chlorine brings it C1, now oxygen will be having 7. So it is demanding 1 more electron. So what happens is going to bond with hydrogen. That kind of bonding, where electrons which are being shared are contributed by one chemical species, you are going to see that special type of covalent bond as a dative bond or coordinate what? Coordinate bond. Now, that one is simple for that, but assuming we have this one of the chlorous acid. The chlorous acid, it means I want to show you where the 2 lone pairs are coming from. These lone pairs, remember, they are the one even pushing the bonds to go down to form a V shape. We shall see the details under the geometry of the what? The molecules, or under the shapes. Now here we are seeing that if chlorine is having the oxidation state 3, as we said here, 3, it means you have used the 3 electrons. Use the 3 electrons. If you use the 3 electrons, you have a balance of 4. Now, how can you use the 3? Now, this is now what the chemistry which I want you to look at. Now, chlorine can also do as other elements are doing what we call promotion of electrons. Promotion of electrons. Other books you can even call it hybridization. So you may find one of the electron here can be promoted to the neighboring vacant orbital. And when it becomes promoted, it comes here. When it comes there, it means here you have remained with how many electrons here? Here there is 1 remaining. This one you have taken it this way, meaning this one is not there. So you have 1, 2, 3. Now, 3 electrons. Now that is when it's going to use the 3 and the balance becomes 2. Now the balance, which is 2, remember, The balance which is 2, it is this one and this one. Now that implies that you have 4 electrons which are redundant. You have used the 3, so 4 are redundant. The 4 which are redundant, they form 2 pairs. The first pair, that is the first pair of 3s, then the second pair of the first 3p, then the 2 pairs like that. And this one is going to become what we call lone pairs. Yes, you have 2 lone pairs. So if you have 2 lone pairs, so you have chlorine having 2 lone pairs there. Then what happens here? These lone pairs which you are having out of the 7, it means the 3 are being used only. You have 4 electrons redundant, but the 3 have been used. How? Assuming this is our chlorine now. Our chlorine, and you have here, you have how many oxygens here? We are seeing 2 oxygens. So you have 1 oxygen here, and you have another oxygen here. What happens? Out of the 3 they are going to use, you are going to bring here 2 electrons. All of them are going to be brought by chlorine. The bond will be dative because the shared electrons are going to be provided by chlorine. Then here, chlorine is bringing it C1, another one, to the oxygen. Remember, this is oxygen, this is oxygen. Now, when you look at this atom of oxygen, is now demanding more one. So you'll find that it becomes attached to hydrogen. Hydrogen brings it C1 there. So this, you find our structure, we are drawing it like that. Not just because you want to decorate, we are drawing it like that. But we want to bring here the image of the lone pair. So lone pairs are those electrons which are remaining. It's a V shape because of these lone pairs pushing this bond down, and even this one pushing it down. That one we are going to look at it under lone pair repulsion, and even bond pair repulsion. Remember, there is even lone pair, bond pair repulsion. That is a chemistry which I can explain that part, which we shall see ahead. Now from there, let me try to look at the last one, the perchloric acid. Perchloric acid, we are saying it is like that. That is our perchloric acid. How are we going to form it? Now we are going to discover that here we are going to use 7 electrons. Position state is 7. 7, all of them. Meaning given here, we are going to do another promotion. We are going to promote 1 there. When we promote 1, we shall put 1 there. Now, so far we have how many electrons? Those are now 5 electrons unpaired. Then what do we do next? We have to promote another one here, to neighboring shell here. So that all of the 7 electrons are going to become unpaired. When we promote, it means the orbitals are going to be like that. The other one of D, that is now 3D. You have 1 there, you have 1 there, you have another one there. But remember, even the S, remember even the 3P, the 3P is still having 1, 1. Those are 6. And remember, even the S is having 1. You have made all of them unpaired. 3D, that is the 3P, and then this is the 3S. Now we have 7 electrons. When you have 7 electrons, assuming you have chlorine in the center here. Chlorine in the center, so if chlorine is in the center, oxygen is yearning for electrons here. We have our oxygen having, configuration of oxygen is 2 to 6. Meaning is yearning for 2. Don't forget, it is the same idea we have applied here, 2 to 6. Meaning, this chlorine here is going to first bring the 2 electrons to this one here. You find it is giving all the 2 electrons to this one. So such that you find here that the oxygen becomes stable here. Similarly, you have another oxygen here. Chlorine gives it 2 still. Then you have another oxygen here. That is oxygen, oxygen, oxygen. Chlorine is giving it 2 more 2. Those are how many? We have 2, 2, then another 2. We add 2 here. Those are 6. Then it means we have to be with another oxygen here to bring out the image of chlorine giving all of the 7. You have given a 6, then there is 1 balance chlorine is giving. So that 1 balance chlorine is giving, it must be now what? You'll find that this oxygen is lacking 1 more electron. So as it is lacking 1 more electron, you will discover that we are going to form now this oxygen atom, the last one. Let me use this one to work properly. So I have to assume that we have 2, and here I add 1. Chlorine gave 1. This one will bring my image proper. So this one, chlorine brought 1 to this, but it brought 2 to this, 2 to this, 2 to this. Those are 6. Then this is the 7th one. then is a demanding one. The one it is demanding, it can only create friendship with what? Hydrogen here. And then the hydrogen brings CTC1 here. And remember, when hydrogen brings CTC1, this oxygen will become satisfied to form those covalent bonds, which are dative. Then from there, this explains why we shall come and do our structure like that. We will draw chlorine in the center, then we put that one like that, even here, even there. Then we put this one and that one, like that. So this one now is going to become a tetrahedral structure. And that is now where, take note of the lone pairs. Here we have lone pair is 0. 0 lone pair. In this one, but in this one, we use how many lone pairs? We add 2 lone pairs, redundant. Totally redundant. Then if we are applying this one here of the CO3, we shall be having one what? One lone pair like that. One lone pair. And that is the chemistry which you have to understand properly. Now, lastly, we go to the acid strength here. The acid strength of those acids is mainly depending on the number of oxygens which you have. The more the oxygen, now we are going to see number of oxygen atoms. Number of oxygen atoms. The more oxygen atoms you have, the more withdraw. The more withdraw of electrons. The more withdraw of electrons from the oxygen. Now remember we have the structure. Take an example, we have a structure like this one. There is a bond between oxygen and hydrogen. Then the more oxygen atoms you have here, the more electrons are withdrawing from the chlorine here. Remember, oxygen is more electronegative than chlorine, based on the size of oxygen. So now to also pulls the what? The electrons. Now in the due course of pulling the electrons, that negative effect, you discover that this bond is going to do what? To weaken. And when this bond weakens, you will see the release of what you call hydrogen what? Hydrogen ion. So we are saying here, the more the oxygen atom, like 4, 3, 2, and so on. So here we have number of oxygen atoms. The more they are, the more we withdraw electrons, and the easier you release. You release the what? Release the electron. Not the electron, you release the hydrogen. The easier you release the proton. This implies what? That perchloric acid is a more strong acid than hypochlorous acid. Why? This one is having many oxygen atoms, 4. This one is having 1 oxygen atom. Therefore, this one is showing a big electronegativity. This one is showing low electronegativity. So here we have less withdrawal of electrons from the chlorine. Here we have a lot of withdrawal of electrons. So here we have a weaker bond between oxygen and hydrogen. Here we have a stronger bond. So here we see easy release of a proton, weaker release of a proton, and so on. So that is the acid strength. And the order will be like this as we are reflecting it there.